Hi class, I just want to do a quick lecture on arc length related to parametric equations. So to find the length of a polar curve in which the radius is some function of theta, in which theta goes from a to b here, we regard theta as a parameter and write the parametric equations of the curve as following. Well, we know x is equal to r cosine of theta. Well, here we're saying we can replace r with f of theta. We know y is equal to r sine of theta, and we're replacing r with f of theta again. So you can use the product rule, and differentiating with respect to theta, you can obtain the following. dx d theta would be equal to dr d theta cosine of theta minus r sine of theta. And dy d theta would be equal to dr d theta sine of theta plus r cosine of theta. If you wanted to find dy dx from these, what you could do is you could just take this equation right here and divide it by this equation right here. Okay, regardless, if we assume that f prime is continuous, we can write the arc length given by this integral right here. Therefore, the length of the curve with polar equations r is equal to f of theta, where theta goes from a to b, a little bit easier. Cleaning this up inside here, if you were to plug in this and this into here and then clean it up, we can use this equation here to very easily find the arc length when you have a polar equation. So length is equal to the integral from a to b, the square root of r squared plus dr d theta squared, and you're integrating with respect to theta. Okay, let's just do a quick example here. So let's find the length of the cardioid where r is equal to 1 plus sine of theta. So here's the cardioid is shown in figure 8. So this is what it would look like here. So what you're going to notice here to find the arc length, we're going to use this equation. Its full length is given by the parameter interval from 0 to 2 pi. Because once you go past 2 pi with this, it's just going to repeat itself again and again. All right, so the formula 5 that we have here, when you plug in here, it's going to be the integral from 0 to 2 pi, the square root. R squared, we're just going to put in the equation for r that you were given here. So dr d theta, obviously when you take the derivative of sine, you get the cosine, and then we're going to square it. So here, we just need to clean this up a little bit. When you clean up underneath the radical here, you get the integral from 0 to 2 pi, square root 2 plus 2 sine of theta d theta. So you could evaluate this integral by multiplying and dividing the integrand by the square root of 2 minus sine theta. If you do that, you'll see that you can evaluate it algebraically. You could also use a computer system for this. In any event, we'll find that the arc length here is equal to 8. So again, just like in the previous lectures, really what this involves is just using the formula and then some algebraic method to be able to evaluate the integral.